All right, welcome everyone to a new talk of the virtual seminar on geometry with symmetries. And today it's my great pleasure to welcome Anusha Krishnan, who's a postdoc at Münster right now, and she's going to talk about positive sectional curvature and Ricci flow. Thanks, Anusha.
Okay, thanks a lot, Ramiro and Emilio and Caroline for the invitation to speak here, and thanks for organizing this very nice seminar series. It's been very great to have this to attend during the pandemic. Okay, so I'll be talking about some joint work with Renato Bettiol on positive sectional curvature and Ricci flow. So here is my plan for the talk. So first I will survey some general stuff about Ricci flow and positive curvature conditions. Then I'll talk about some past work that we did on non-negative sectional curvature under the Ricci flow in 4 dimensions. So I'll talk about that a little because that is the basis for our new work on how positive sectional curvature behaves under Ricci flow in dimension 4. And yeah, so these 2 parts of the talk are the parts that will have the geometry with symmetries. So specifically cohomogeneity 1. Okay, so let me get started. So the Ricci flow is the following geometric PDE for evolving a Riemannian metric. So G of t is a Riemannian metric evolving with time by negative twice the Ricci tensor, starting from some initial metric G0. And so the Ricci tensor the Ricci operator on a metric is a second order differential operator. And in certain special coordinates, this looks like the Laplacian of the metric. So one generally thinks of this as a heat type equation for the metric. And so as a result, one would expect it to preserve lower bounds. So the heuristic expectation we might have from the Ricci flow is that it preserves lower bounds on curvature. And this is true in several cases. And this aspect of the Ricci flow is a key in various recognition type theorems, by which I mean all these theorems have some assumption of positive curvature on the metric, on the manifold. The manifold admits some metric of positive curvature in some sense, then it must be diffeomorphic to a spherical space form. So starting with Hamilton's original theorem in the 80s on positive Ricci curvature and positive curvature. So positive Ricci curvature in dimension 3 implies that the manifold is diffeomorphic to a spherical space form. Later he extended this to positive curvature operator being a sufficient condition in dimension 4. And then later with Wilking's extension of this result to two positive curvature operator in all dimensions, and then also Brendel-Shane's sphere theorem. So all follow this kind of, if the metric has positive enough curvature in some sense, then use the Ricci flow to show it must be diffeomorphic to a spherical space form. Okay, so one easy way to see this is to look at the scalar curvature. The scalar curvature evolves by the following evolution equation. So ddt of scalar is Laplace of scalar plus this forcing term, which notice is always non-negative. And so the maximum principle implies that a lower bound on scalar curvature, in particular non-negative scalar curvature, is a condition that is preserved under Ricci flow. Okay, Hamilton's tensor maximum principle allows one to bump this up to tensors, and that is the essential ingredient in showing that non-negative curvature operator that is preserved under the flow in all dimensions. Okay, and talking specifically about the condition of non-negative sectional curvature. again, in Hamilton's work, he showed that non-negative sectional curvature is preserved under the Ricci flow on closed 3 manifolds. And that is the first step in his theorem to show that positive Ricci curvature implies diffeomorphic to spherical space form. However, in 2004, Delaney gave an example of a non-compact 4 manifold where positive sectional curvature is not preserved under the Ricci flow. And compact examples came not so long afterwards. And these are homogeneous examples. So due to Bohm and Wilking, so they showed that there exist homogeneous metrics on the 6 and 12 dimensional flag manifolds shown here. So homogeneous metrics which evolve under the Ricci flow to metrics with mixed sectional curvature. So, right, so important to note is that the isometry group of a manifold remains unchanged under the Ricci flow. So if you start with a homogeneous metric, it remains homogeneous, and the Ricci flow reduces to an ODE in this case. Right. Also, these examples of Bohm-Wilking were extended by work of Chung, Wallach, and also Abiev, Nikonorov, where they show that, in fact, this is the generic, this is the behavior for all generic homogeneous positive sectional curvature metrics on these flag manifolds, and also the 24-dimensional one. So a generic homogeneous metric of positive sectional curvature on these manifolds loses the property of positive sectional curvature when evolved under the Ricci flow. So in particular, one knows that
Anusha, do you remember what do you mean with generic in this case?
Yeah, so these homogeneous metrics, they are determined by 3 parameters. So under the isotropy representation, it splits into 3 modules. I think generic means all three components are different. That is does that make sense?
Okay, thank you.
Okay.
So the by invariant is not generic. It should be, right? Because
yeah, it is. Yeah.
Okay.
Yeah. Okay. Right. So in particular, positive sectional curvature, non-negative sectional curvature, these are not preserved under the Ricci flow. We have these examples in dimension 6 and above. Okay, let me talk a little about positive curvature cones. So the curvature operator at a point is a symmetric endomorphism on bivectors, and positive curvature conditions, they correspond to cones inside the inside this vector space, which is symmetric endomorphisms on bivectors, which also satisfy the Bianchi identity. So this is the space of algebraic curvature operators. And if one looks at how the curvature operator evolves under the Ricci flow, then it satisfies the following PDE. So this is a heat type equation with some quadratic, with some forcing term which is quadratic in the curvature operator. So this math cal R is curvature operator. And if one looks at the corresponding ODE, where one drops the when you drop the Laplace term. So if you just look at this as an ODE on a single tangent space, okay, this is the Ricci flow ODE. And what Hamilton's tensor maximum principle says is that if if C is a cone that is preserved by the Ricci flow ODE here on the right, then the corresponding curvature condition defined by this cone is Ricci flow invariant. And this is the ingredient in proving that various curvature conditions like positive or non-negative or two positive curvature operator, etc., are Ricci flow invariant. This is the basic ingredient in that. And Wilking in 2013 gave a Lie algebraic approach, which gives a unified proof of all the previously known Ricci flow invariant curvature cones by showing that a curvature cone, which is invariant under the okay, so wedge 2 of Rn is you can think of as the Lie algebra SON, and thinking of cones that are defined by subsets invariant under the adjoint action, such cones, such sets yield you invariant Ricci flow invariant curvature conditions. Okay, by looking at the curvature operator of a specific example, in particular Fubini's 2D metric on a CPN, one can show that the cone of non-negative sectional curvature operators, this is not invariant under the Ricci flow ODE. Okay, and being invariant under the Ricci flow ODE is a sufficient condition for the curvature condition to be Ricci flow invariant under the PDE. It's not clear that it's necessary. Here is another interesting result due to Richard and Seshadri, where they showed that in any even dimension, the cone of non-negative scalar curvature operators, this is the only Ricci flow ODE invariant cone which contains the cone of non-negative sectional curvature operators. Okay, so in even dimensions, if there's a Ricci flow invariant curvature cone containing the cone of non-negative sectional curvature operators, it must be the non-negative scalar curvature cone. Okay, so this is all kind of evidence that non-negative sectional curvature ought not to be preserved under the Ricci flow in general. And we saw some examples on the previous slide in dimensions 6 and up. Of course, that leaves open dimension 4 in particular. And before I state the main theorem for today, in some previous work with Renato Bettiol, we showed that there exist metrics of non-negative sectional curvature on each of these 4 manifolds. So the 4-sphere CP2, S2 cross S2, and CP2 connect some CP2 bar, which immediately lose the property of non-negative sectional curvature when evolved by the Ricci flow. And as a corollary of this, by taking products with spheres, this shows that non-negative sectional curvature is not preserved under the Ricci flow in dimensions 4 and up. So some comments about these, the manifolds in this theorem. So all 4 of these 4 manifolds, S4, CP2, S2 cross S2, and CP2 connect some CP2 bar. So each of them admits a cohomogeneity 1 action by the Lie group SO3, and the structure of the orbit structure of the manifolds under this group action, they have something in common, which allowed us to give a unified proof for all 4 at the same time. Another comment is that along with CP2 connect some CP2, which does not admit a cohomogeneity 1 action. These 4 are the only simply connected 4 manifolds known to admit metrics of non-negative sectional curvature. And so our theorem showed that for each of these, there are some non-negative sectional curvature metrics which lose the property of non-negative sectional under the Ricci flow. Now, of course, it's a difficult problem in geometry, which manifolds admit metrics of positive sectional curvature. And of these 4 manifolds listed in the theorem here, only the first 2 are known to admit positive sectional curvature metrics. And so the main theorem I want to talk about is recent work with Renato Bettiol, where we show that S4 and CP2 admit positive sectional curvature metrics, which evolve under the Ricci flow to metrics with sectional curvature of mixed sign. Okay, so note that the standard metrics on these manifolds, so for S4, the standard metric is the round metric, and on CP2, the Fubini's 2D metric. These are Einstein metrics, and under the Ricci flow, Einstein metrics just evolve self-similarly. So in particular, if you were to take those as the initial positively curved metrics, that would not be a good choice if you wanted to break positive sectional curvature under Ricci flow. So these metrics that we use in, that we produce in this theorem, they are in some sense kind of far from the standard metrics on these manifolds. Okay, so that is the main theorem that I want to talk about today. The proof of this theorem, of theorem 1, uses the proof of theorem 0. So I will speak briefly about that. And everything works within the setup of cohomogeneity 1 actions. So let me say a little about that. Are there any questions before I move on?
Yes, Anusha, is it not the case that CP2 connected some CP2 has a cohomogeneity 1 action?
Yeah, it does not. Yeah.
It does not. Okay. Thanks.
Okay. Right. So let me speak a little about cohomogeneity 1 manifolds. So the setting is of a Lie group G acting on a Riemannian manifold, acting isometrically, so that the orbit space M quotiented out by G is 1-dimensional. And for the purposes of this talk, M quotiented out by G is going to be a closed interval, 0L. Here is a schematic picture of a cohomogeneity 1 manifold, where this black curve is a horizontal lift of the orbit space inside M. So M is foliated by these orbits. Each orbit is, so it's the orbit under group action. It's isometric to a homogeneous space, which is the same homogeneous space G mod H for pre-images of points in the open interval 0L. These are called principal orbits. And G mod K minus and G mod K plus corresponding to pre-images of the endpoints of the interval. Okay, so this data, the Lie group G, as well as these isotropy groups H, K plus, and K minus, all that bundled together is called a group diagram for this cohomogeneity 1 action. Okay, a little more about the structure of a cohomogeneity 1 manifold. By using the slice theorem, you can show that K plus or minus quotiented out by H must be spheres. So these are normal spheres. So take this point on this singular orbit. This is a normal sphere at that point. K minus acts transitively with isotropy H, and that's why you have this statement that K plus or minus mod H must be spheres. And this also gives further structure to the cohomogeneity one manifold, which is that it can be written as the union of disk bundles over the singular orbits. So the union of nu minus and nu plus, where nu plus or minus are these disk bundles over the two singular orbits, and they are glued together along a principal orbit, which is the boundary of the two. Right, so that's a cohomogeneity one manifold in general. Let me specialize to the case of S4. Right, and so theorem 0 talks about 4 manifolds, S4, CP2, S2 cross S2, and CP2 connects some CP2 bar. Since the proof works similarly for all of them, I'm going to focus on S4. So here is the action. SO3 acts on R5 in the following way. So SO3 acts on the space of 3 by 3 matrices, which are symmetric and traceless. SO3 acts by conjugation, and you can count the symmetric 3 by 3 matrices. That makes it a 6-dimensional space, and asking for traceless reduces the dimension one more. So that's an R5. And it acts in a way that preserves preserves lengths. And so this descends to an action of SO3 on S4. So that turns out to be a cohomogeneity one action. Here is a schematic picture. The generic orbits are some S3 quotiented out by the order 8 group of quaternions, and the singular the isotropy groups at the singular orbits are O2s, orthogonal groups, and the singular orbits are RP2s. So invariant metrics on such a manifold, just by the symmetries, it's enough to specify the invariant metric along this black curve, which is some minimal geodesic between the singular orbits. And an invariant metric can be written in this form. So R is the variable that parameterizes the orbit space, and G sub R is a homogeneous metric on the principal orbit, which depends on R. For this particular case of SO3 acting on S4, the homogeneous metric on the principal orbit can be diagonalized all along the geodesic in a common orbit of Killing vector fields, and it has this diagonal form where so phi, xi, and psi are the lengths of Killing vector fields along the along this minimal geodesic. So these are all lengths in the direction of, along the principal orbit. So in the picture on the right, you see what phi, xi, and psi look like for the round metric. So the round metric on S4 is in particular an invariant metric under this cohomogeneity one action, and it is given by functions phi1, xi1, and psi1, which are in this case they are some trigonometric functions, some combinations of sines and cosines. Okay, now we come to this very nice and important theorem due to Grove and Ziller, where they show that a cohomogeneity one manifold with co-dimension to singular orbits admits invariant non-negative sectional curvature metrics. So this was a big leap forward in constructing metrics of non-negative sectional curvature. So how it works is, remember that a cohomogeneity one manifold has a decomposition into disk bundles over the singular orbits, and their construction goes by constructing non-negative sectional curvature metrics on these two disk bundles in such a way that they can be glued smoothly to give a metric on the whole manifold. And so in general, the isotropic groups at the two singular orbits could be different. These two disk bundles, I mean, the disks, the fibers in the disk bundles could be of different dimensions. So how do you construct something in such a way that you can glue together? And the way that is done is to ensure to make the construction in such a way that the metric on the boundary of the disk bundle or in a tubular neighborhood of the boundary is a product metric of the interval with the normal homogeneous metric on G mod H on the principal orbit. So you have, I mean, no matter what is happening close to the singular orbits, but close to the principal orbit on the two sides, the metric is interval product with normal homogeneous metrics, and so you can glue them together. And this construction works if the cohomogeneity one manifold has codimension two singular orbits. They use this to construct non-negative sectional curvature metrics on exotic 7 spheres. And yeah, so recently there has also been many nice extensions of that work to all exotic 7 spheres. And this, if you look at this cohomogeneity one action on S4, it has, you notice, codimension two singular orbits. So it admits such a Grove-Ziller metric. And here is a picture of what the Grove-Ziller metric on S4 looks like. So it's still determined by functions phi, xi, and psi, except if you compare with the picture above for the round metric, it looks like you kind of flattened out those functions. And notice this corresponds to the fact that you define the metric on the two disk bundles in such a way that you can glue smoothly in the middle by ensuring that it is a product near the middle of the manifold. Okay, so this is the Grove-Ziller metric on S4, and this is our starting point for proving theorem 0. So theorem 0, remember, said that you have non-negative sectional curvature metrics on S4 and the 3 other manifolds, which lose that property under the Ricci flow, which lose non-negative sectional under the Ricci flow. So here is a proof of theorem 0. You start with the initial metric being the Grove-Ziller metric and evolve it by the Ricci flow. The sectional curvature of a two-plane, a horizontal two-plane, so spanned by X3 and DDR. So DDR is a direction along the minimal geodesic between the, so the one that is transverse to all the principal orbits, and X3 is a direction along a principal orbit. So such a horizontal two-plane. Its sectional curvature is given by the following expression, where psi is the length of the Killing vector field X3. So if you look at the picture of the Grove-Ziller metric, notice that that close to r equals 0. Actually, the function psi over here is just constant throughout the length of the interval. So if you have such a two-plane mu, which is the span of X3 and DDR, then its sectional curvature is just dead 0. Recall also that the isometry group of the manifold remains unchanged under the Ricci flow. And so we retain the cohomogeneity one structure, and the Ricci flow becomes the following system of PDEs in these functions, phi, xi, and psi. So it looks like some second derivative term plus terms of lower order, which I didn't write. Also, I'm lying slightly here because you also have to introduce one more function corresponding to a possible change of parameterization of the minimal geodesic under the Ricci flow, but modulo these details, this is what the Ricci flow looks like. It corresponds to these coupled PDEs and the functions phi, xi, and psi. And using these, we can compute the first variation with respect to time of the sectional curvature of such a two-plane mu. So using these the expressions in these PDEs, we can compute this first variation. So it's the DDT, it's DDT of this expression at time t equals 0. I'll spare you the messy computations. It turns out that this is negative for r small enough. So if you're close enough, so r small means you're very close to one singular orbit. And if in that case, we show that this first variation is negative. I started off 0. So that means for all small enough times, this two-plane has negative sectional curvature. And that is the proof of theorem 0. So yeah, basically we use the Grove-Ziller metric and show that the nice thing about the Grove-Ziller metric is they are non-negatively curved, but they have lots of flat two planes. And we use one of those flat two planes and show that it turns negative. For the, yeah, and the proof works exactly the same way for the other three manifolds. Okay, now you're interested in extending this to the situation of positive sectional curvature. And the, well, so the nice thing working for us here is that we had all these flat two planes and you just have to look at the first variation in time at such a flat two plane. But if you want positive curvature to turn negative, you need to flow for some time. And so the question was what metric to choose on S4 or CP2. And so let me speak about the proof of theorem 1. The proof of theorem 1 relies on the following result that we show. We show that every Grove-Ziller metric on S4 or on CP2 is the smooth limit of cohomogeneity 1 metrics, which are positively curved. So the Grove-Ziller metrics are, they have non-negative sectional curvature, but we show that you can find cohomogeneity 1 metrics arbitrarily close to them, which are positively curved. Okay, using theorem 2, how do you get theorem 1? Theorem 1, remember, says roughly that positive sectional curvature evolves to some mixed sectional curvature. So some positively curved two-plane turns negative. So we use the continuous dependence of the Ricci flow on initial data, which you can show either by Hamilton's compactness or in our preprint we cite the recent paper of Pauhard, Kunther, and Eisenberg. And basically, continuous dependence of the Ricci flow on initial data says that if the initial metric is close to G0, then the so if initial metric GS is close to G0, then the evolved GS of t is close to G0 of t. So if it was close enough at the start, it stays close as it evolves.
Hi, Anusha. So yeah, for the matrix GS, is the cohomogeneity action the same one?
Yeah, the same.
Okay.
Yeah, I'll on the next in a slide or two I'll say how those are constructed.
Okay.
Mm-hmm. Okay, and so the proof of theorem 0 on the previous slide told us that we have these two planes which were initially flat, which were flat for the Grove-Ziller metric G0, and they turn negatively curved for small enough positive times. So using these metrics that we construct in theorem 2, this tells us that for S small enough, the evolution of the metric GS, its sectional curvature is going to be close to that of G0. And so for S small enough, GS is going to acquire negative curvature on the two-plane mu. And that is the proof of theorem 1. So our main ingredient here is the continuous dependence of Ricci flow on initial data, and our perturbing the Grove-Ziller metrics on S4 and CP2 to metrics of positive sectional curvature. So in the remainder of the talk, I will tell you how we do that, how we perturb these metrics to positive sectional curvature. Okay, so before I go to perturbing the metrics on S4 and CP2 as warm-up, let us go one dimension lower and look at the cohomogeneity one action of T2 on the three-sphere. So think of the three-sphere sitting inside a complex two-dimensional space, and the two torus acts just by by circles rotating in each complex coordinate. This is a cohomogeneity one action where the generic or principal orbits are two tori collapsing at either end to circles in orthogonal two planes inside R4. And an invariant metric is given by a similar type of formula as we had on the previous slide, except here it's determined by two functions on the orbit space, phi and xi. And here is a comparison of the Grove-Ziller metric and the round metric on S3. Right, as I mentioned, the singular orbits are circles which have codimension 2 inside S3. So you have a Grove-Ziller metric for this action as well, and this is what it looks like. So again, heuristically similar picture as previous, except we just have two functions. For the round metric, these are some trigonometric functions, and for the Grove-Ziller metric, they are flattened out. All right. Now the curvature operator in this setting is diagonal with these entries, and since we are on a three manifold here, you have a non-negative sectional curvature if and only if you have non-negative curvature operator, and that you have if and only if phi and xi are concave and monotone. Or if you ask for positive sectional curvature, then you need these functions to be strictly concave and monotone. All right. So now it's not so difficult to see what we can do. If we wanted to perturb this Grove-Ziller metric to positive curvature, you can just define a new metric by taking a convex combination of the lengths. That is a convex combination of the lengths of these Killing vector fields. That's what we do here. S is some number between 0 and 1. And it's easy to see that for all positive numbers S, phi S and xi S are going to be strictly concave and monotone. And so GS has positive sectional curvature for all S positive. So that was perturbing the Grove-Ziller metric on S3 to one of positive sectional curvature. And this motivates what we do in dimension 4. Okay, and theorem 2 talked about S4 and CP2. Again, I'll focus initially just on S4 and then say what we do differently for CP2. So here are the Grove-Ziller metric and the round metric for S4. So right, the nice thing here is on S4, we already have one nice metric of positive sectional curvature. Again, we define a new metric GS by taking convex combinations of the corresponding lengths of Killing vector fields. Okay, so if you have these phi s, cs, and cs, they still define a smooth metric on S4, and we claim that for small enough s positive, this metric GS has positive sectional curvature. Right. So on the previous slide, we had that for all s that you choose between 0 and 1, the metric GS has positive curvature. Here we just managed to show it close enough through the Grove-Ziller metric, but okay, that's what we show here. The major difficulty compared to the previous slide is that in dimension 4, non-negative sectional curvature is not equivalent to non-negative curvature operator. Okay, that's a bit of a bummer, but what we do have is Thorpe's trick, which I state over here. So if you look at an algebraic curvature operator, okay, so this is something happening just on one tangent space, then R, this algebraic curvature operator, it has positive or non-negative sectional curvature if and only if you can find some real number tau, so that R perturbed by tau times the Hodge-star operator, that is positive definite or non-negative definite. Okay, so notice that R is an algebraic curvature operator. It's a symmetric endomorphism on bivectors. So is the Hodge-star operator in dimension 4. And what Thorpe's trick says is that if you perturb, I mean, you don't asking that R itself R itself is a positive definite would be asking too much in dimension 4. But if you can perturb R by some multiple of the Hodge-star operator so that is positive definite, that's enough to yield you that R has positive sectional curvature. And right, in general, in higher dimensions, what Thorpe's trick says is just that if you can perturb R by a 4 form, perturb the curvature operator by a 4 form so that it is positive definite, then the original curvature operator had positive sectional curvature. In dimension 4, what's nice is that this condition becomes if and only if, and that in dimension 4 you have only one, up to multiple you have only one 4 form. So really what you're looking for is just a real number tau. Okay, so here I just put up Thorpe's trick again. Now G0 for me is the Grove-Ziller metric on S4. That is a metric of non-negative sectional curvature. So by the above characterization in Thorpe's trick, we know that there must be some number tau on each tangent space, so that on each tangent space you can perturb the curvature operator to be non-negative definite. And since we are working in the setting of cohomogeneity 1, we can assume that T0 is, you can choose the T0 as a function on the whole manifold to be compatible with the cohomogeneity 1 action. So you're really just looking for a real valued function on the orbit space. Okay, so we already know that Grove-Ziller metric has non-negative sectional curvature. So we know that we have such a T0. And in fact, it's possible to explicitly write down this T naught in terms of the function phi naught that appears in the Grove-Ziller metric. So phi naught is the function that vanishes at one singular orbit. We can write, we can express the function T naught on the orbit space in terms of that phi naught. Notice also that there's some symmetry about the midpoint of the orbit space here. So it's enough to define things just on half of the interval. It's okay, so it's not a real symmetry, but it's that phi naught and xi naught, they kind of switch roles. All right. Again, the nice thing in 3 dimensions was that the curvature operator was diagonal. Here it's not diagonal, but it is block diagonal with 3 2x2 blocks. And now if you look at the curvature operator of the metric G sub S, the perturbed Grove-Ziller metric, its entries are functions now of S and R. And by looking at the Taylor expansions of the curvature entries with respect to S and R, we are able to pick a suitable choice of tau. So tau is an order S perturbation of the tau naught, which was the function for the Grove-Ziller metric. So we are able to choose a suitable perturbation of the Thorpe function for the Grove-Ziller metric, so that this perturbation of the curvature operator of GS becomes positive definite for S sufficiently small. And that completes the proof of theorem 2 for S4. So basically we used that S4 already, like we already know that S4 admits some positive sectional curvature metric, the round metric in this case. We use that as a direction to perturb the Grove-Ziller metric. And we use Thorpe's trick to show that actually for small enough such perturbations in this direction, the resulting metric actually has positive sectional curvature. For CP2, also, we have a nice canonical positively curved metric, which is the Fubini-Strudi metric. The proof for CP2 goes by perturbing the Grove-Ziller metric on CP2 in the direction of the Fubini-Strudi metric. So the proof goes more or less similarly. The group diagram over there is slightly is not so symmetric about the midpoint of the interval. So we need to do a slightly different analysis on the 2 parts of the interval, but basically it's the same idea. Okay, here are some remarks. The same result in higher dimensions is not an immediate corollary because unfortunately positive sectional curvature is not preserved under metric products, unlike non-negative sectional curvature. Another comment about higher dimensions. So I said that Thorpe's trick in higher dimensions is not so easy because the space of 4 dimensions, the space of 4 forms there has bigger dimension. You have more than just the volume from as for a 4 manifold. So it's not quite clear there which direction to perturb the curvature operator in. Also, if you wanted to say follow this same idea of proof, you'd want to start with some nice cohomogeneity 1 action, or say this nice disk bundle decomposition, and use the round metric on a sphere as a direction to perturb in. But unfortunately, this is not possible on spheres of dimensions bigger than 7, because due to this result of DeVito, Garcia, and Kerin, spheres of dimension bigger than 7 cannot admit double disk bundle decompositions with codimension 2 singularlies. So yeah, that's bad news for this. If you wanted to use the same scheme of proof with Grove-Ziller metric and use the round metric on spheres. One more comment is that we do here a first order perturbation of a non-negative sectional curvature metric to attain positive sectional curvature. This in general is a very difficult thing to do. And it's often the case that you have some obstructions, even for example, if the initial metric contains a flat, totally geodesic embedded torus, you can use the Gauss equations for that relate the curvature of submanifold with the bigger manifold. You can use that and Gauss-Bonnet to show that such a first order perturbation is obstructed in this case. That's the case, for example, for the Grove-Ziller metrics on S2 cross S2 and CP2 connects some CP2 bar. Of course, there by Shankliner, we already know that we could not obtain a cohomogeneity one positive sectional curvature metric, but here's just some more perspective. Also, this kind of perturbation is obstructed, for example, for the Grove-Ziller metrics on these PQ families of 7-dimensional cohomogeneity one candidates for positive sectional curvature. Yeah, so even there, so this example of positive sectional curvature on the unit tangent bundle of S4, that somehow is that metric is somehow far from the Grove-Ziller metric. Okay, some related further questions. It would be interesting to find an odd dimensional example where positive sectional is not preserved under Ricci flow. So all our examples in this work, as well as all the previously known examples, are in even dimensions, and also referring to the result of Richard and Seshadri, it would be interesting there to find odd dimensional examples. For our work here, we don't know the answer, but it would be interesting to know whether this metric GS has positive sectional curvature all the way up to the round metric. So the round metric has positive curvature close to Grove-Ziller, it does, but we don't know what happens in between. And a related question that I'm interested in, if any of you know something about this, I'd be very interested to hear about, is what can we say about the topology of the space of non-negative sectional curvature metrics on S4? Is it connected, for example? This also refers to question 2 here. Yeah, even for the case of, say, positive scalar curvature metrics on S4, what is the topology of that space? I don't think it's known. These would be interesting further questions. All right, so thank you very much for your attention.
Thanks, Anusha, for a very nice talk. Are there any questions or comments for the speaker? I think with those remarks and open questions, you took away most of my questions, Anusha.
Oh, okay.
Is there anyone there with a question? So why is it the case that all examples are with even dimension? I mean, what fails in your method if you take the, say, 7-dimensional positively curved examples, or it's just impossible to compute? Like,
yeah,
could you look at
maybe
the examples in dimension 7 and say take approach a metric with some 0 planes and then argue, as you argued in the theorem 0? You know what I mean? That would be the strategy, right?
So theorem 0, that works in higher dimensions. So if you have a Grove-Ziller metric. Yeah, that theorem that flat two planes, they turn negatively curved immediately, that works in higher dimensions. The question, at least on suitable cohomogeneity one group diagrams, the question about perturbing, like having a suitable Grove-Ziller metric and being able to perturb it to positive sectional curvature, that yeah, that is a challenge. Maybe for, so the result I mentioned about yeah, this not having double disk bundle decompositions with codimension 2 singular leaves, that is on spheres of dimension bigger than 7. Maybe dimension 5 or 6 or 7, this could still be investigated. Yeah, I guess there it's that finding a suitable group diagram with codimension 2 singular orbits, as well as implementing Thorpe streak would be more challenging there. Yeah.
So the problem is always finding metrics of positive sectional curvature.
Yeah. That's as you know,
Always the crux.
non-trivial problem.
Right.
Yeah.
Any other
Hi,
questions or comments on Anusha? Johan?
Yeah. So for the higher dimensional cohomogeneity one candidates with positive curvature, for example, the 7-dimensional ones, do you have examples that these metrics are really diagonal? Because as far as I can recall, it seems like the diagonal metrics are kind of special.
Yeah, that's true. Yeah, I don't know. Yeah, probably they're not diagonal. Yeah.
Oh, okay.
Also, I meant to ask in the theorem 0, when you run the Ricci flow, how do you know that these metrics are going to be diagonal with respect to the same frame? Or do you
We
have
use
to move the
symmetry.
frame?
Yeah, that's true.
You don't have
question-
enough symmetry, right? You only have SO3 symmetry. You don't have SO4 or like.
We have enough symmetries in that the so if you look at the action of SO3 on S4, then the isotropic group at the principal orbit, that is large enough, that has enough symmetries that any invariant metric.
This Q, okay.
Yeah.
Mm.
Yeah.
Right. Excellent. Okay, if there are no more questions, we can thank Anusha again for a nice talk.
Thanks for having me.